Hello, I'm Maurice Dupre, and in this section we're going to discuss continuity. Let's look first at the definition of continuity. A function f of x is continuous at x equals c if and only if it meets the following three conditions. First, f of c exists. That means c lies in the domain of the function f. Second, the limit as x approaches c of f of x exists. That means f has a limit as x approaches c. 3, the limit as x approaches c of x equals f of c. That is, the limit equals the function value. Now, notice what this means for the computation of limits. When I know in advance that the function is continuous at x equals c, if I'm presented with the problem of computing the limit as x approaches c of f of x, then this third condition tells me, well, all I have to do is plug c into the function. So consequently, it's very useful to be able to spot continuity. Well, let's be a little more careful about what we mean by this limit, because remember, when we have interior points, we do have two-sided limits, so continuous at an interior point c of its domain means the limit as x approaches c of f of x equals f of c. But at the endpoint, a function y equal f of x is continuous at a left endpoint a or is continuous at a right endpoint b of its domain if the limit as x approaches a from the right of f of x equals the left endpoint value f of a, or the limit as x approaches b from the left of f of x equals f of b. So here we are on the right edge of the domain, and so we must approach that right endpoint from the left. Over here, we're on the left endpoint of the domain, so staying within the domain, we must approach that endpoint from the right. And so if those one-sided limits exist and give the values at the endpoint, for instance, if the left endpoint value is the one-sided limit at the left endpoint, we say it's continuous at the left endpoint A, and likewise, respectively, here for the right endpoint. Now, with our limit theorems, we know we can apply them to get the same types of theorems about continuity. So, for instance, if f and g are continuous at x equals c, then the combination sum, difference, products are also going to be continuous, just because our sum rule for limits tells us that the sum of f and g will have limit as x approaches c, f of c plus g of c, and likewise the difference in the product. And likewise, if we have a constant k and we multiply our function f by that constant k, then we still get continuity at the point c. Likewise, for a quotient f over g, provided, remember, that g of c is not 0. Now, why would g of c be required not to be 0? Well, remember, our quotient rule for limits says the limit of a quotient is the quotient of a limit, provided that the denominator limit is non-zero. Well, if g is continuous at c, the value of that limit is g of c. And so now all we have to do is look and see if the value of the function is not 0 at c, then f over g is continuous at c if both f and g are. As far as powers are concerned, we can raise a continuous function at c to any rational power r over s, and we will get a function which is continuous at c, provided it is defined on an open interval containing c, where r and s are integers. Now, another thing that we often do with functions is substitute one function inside another, and here, knowing a function is continuous is a big advantage. If g is continuous at the point b and the limit as x approaches c of f of x equals b, then the limit as x approaches c of g of f of x equals g of b. So that means g of the limit is the limit of g of the function. In other words, g of the limit of f of x is the limit of g of f of x. We're in effect being able to interchange limits and the outer function here if that outer function is continuous. Well, in particular, that would mean if the function f is continuous at x equals c, this b would in fact be simply f of c. And so in that case, we get a rule for composite of continuous functions. If f is continuous at c and g is continuous at f of c, then the composite G composition F is continuous at C. So in other words, we have a lot of ways to combine here and get continuous functions. We say a function is continuous if it's continuous at each point of its domain. Let's look at our combination rules for continuity at a single point and see what we can say about combinations of continuous functions. So here, if f and g are continuous and not just at x equals c, then the sum of f and g would be continuous because why? At each point now, c in the domain of f plus g, well, f is continuous at c, g is continuous at c, so f plus g is continuous at c. And so consequently, the continuity would apply to the sum at each point where the sum is defined. Likewise, the difference, and likewise, the product. Now, constant multiples, of course, that will work too. If f is continuous at each point of its domain, then so is the constant multiple of f. And what about the quotient? Remember, f divided by g is continuous at c, provided g of c is not 0. But notice, if g of c is 0, then c cannot be in the domain of f over g. And so consequently, the quotient is again continuous at each point of its domain. How about for powers? The power f to the r over s is continuous at x equals c, provided it is defined on an open interval containing c, where r and s are integers. Well, that's just where the function is defined for the case where f itself is non-negative, and in the case where f is negative, of course, it'll be defined for certain odd powers. But in any case, if that is the case, that f is defined on an open interval, then if f is continuous on that open interval, so will f raised to that power. Now, in the case of, for instance, the square root function, in fact, it is easy to see that it's continuous at 0 from the right, and so it's continuous. And so consequently, the powers will generally be continuous. What we have to do is examine carefully in the case where we have closed intervals looking at endpoints. Now, again, since the composite of continuous functions will be continuous at c if the input function f is continuous at c, then so g composed with f is continuous at c. And so consequently, what we now see is that if f is continuous on its domain and g is continuous on its domain, then g composition f would be continuous. So now the end result is we can multiply, add, subtract, divide, and compose continuous functions, and the results will always give us continuous functions, because in effect the only time problems occur is where the combination leads to having to throw something out of the domain, for instance, dividing by 0. And so consequently, all we have to do when we look at algebraic expressions is examine the domain. Let's see how we can use our rules for combining continuous functions to get more continuous functions to apply to problems. Tell where continuous. Well, let's look at this expression, y equals 1 over x minus 2 minus 3x. So that defines a function of x. Where would it be continuous? Well, notice, as long as x is not equal to 2, then our quotient rule for limits tells us the first term has a limit at whatever value of x we approach. Likewise, the second term. So in effect, we're continuous on the entire domain of the function, which is all x not equal to 2. Notice the basic function f of x equals x is continuous. And so what's being done? First, we're taking this continuous function f of x equals x and multiplying by 3. We're taking it and subtracting 2. Then we're dividing 1 by x minus 2. So division of continuous functions results in continuous functions, and then we're taking a continuous function here and subtracting another one. So the result will be a continuous function on its entire domain, and so where it's continuous is simply on its entire domain, which is, of course, all x not equal to 2. Let's look at the next expression. Y equals the quantity x plus 1 divided by the quantity x squared minus 4x plus 3. Now, when we see this expression, we know, of course, polynomial down here, there's a possibility that it has some roots and so could be 0 for certain values of x. On the other hand, our quotient rule for continuous functions tells us that the quotient of continuous functions is again continuous wherever it's defined. And so consequently, this function will be continuous on its entire domain. What is the domain? All x for which the denominator is not 0. Well, of course, we find that by factoring. So when we do that, notice when we put x equal to 1, we get 1 minus 4 plus 3 is 0. So x minus 1 is a factor. And the other factor is easily seen to be simply x minus 3. And so where will the denominator vanish? At x equal 1 or x equal 3. So we have to have x not equal to 1 and x not equal to 3. That's the entire domain of this function. It's continuous at any x not equal to 1 or 3. Here we have the square root function with 2x plus 3 put inside it. So here's a case where our composite of continuous functions being continuous comes into play. And of course, the square root function is continuous at x equals 0. If we look at the square root function itself, we know its graph, in effect, is half a parabola over on its side. And so remember to check continuity at the left end. We simply look at the limit as x approaches 0 from the right, and that's clearly 0. So the square root function is continuous, and putting in 2x plus 3 then results in a continuous function as long as the input is not negative. So here we have to have the condition 2x plus 3 greater than or equal to 0, which is, of course, the same as x greater than or equal to negative 3/2. So here, this expression gives a function whose domain is all x greater than or equal to negative 3/2, and it would be continuous on that domain. Remember, the basic idea of a limit of f of x as x approaches c is to tell us, in some sense, what the value of the function should be at c, irrespective of what it really is. So consequently, we can always ask, can the function be defined at x equals c so as to be continuous, even if the point c is not in the domain? Let's look at an example. Define g of 3 in a way that extends g of x equals x squared minus 9 divided by the quantity x minus 3 to be continuous at x equals 3. Notice, as it stands, x equal 3 is not in the domain of this function. But notice when I look at the expression defining g of x, the x squared minus 9 divided by the quantity x minus 3, I can factor the numerator as x minus 3 times x plus 3. And so we have the quantity x minus 3 multiplied by the quantity x plus 3, all divided by the x minus 3. Notice what I can do at this point. I can cancel the x minus 3's and end up with the expression x plus 3. Now notice, this equation is an equation which is true for all x not equal to 3. On the other hand, when I look at this expression right here, there's a continuous function on the whole real line. It makes sense for every real number. And so consequently, in effect, this expression is giving us an extension of the function which includes the number 3 in its domain. And so consequently, when I look at that expression, I know the limit as x approaches 3 of x plus 3 is simply 3 plus 3, which is 6. And so consequently, we can see now that what I have to do is define g of 3 to be 6. Notice, if this expression is equal to this expression for every x not equal to 3, since the limit operation as x approaches 3 has nothing to do with the value of the function at 3, only with other values of x, that means these two have to be equal, have the same limit, that is, at 3. So I can put limit of x squared minus 9 over x minus 3 equals limit as x approaches 3 of x plus 3 equals 6. And so what we see here is that the way to define g at 3 is to make it exactly equal to 6. Once I've made that definition, g is now continuous at x equals 3. Since it's obviously continuous at every other x, now the function would be continuous on the whole real line. Generally speaking, when I have an algebraic expression, such as a quotient of two polynomials, and there's a point where the denominator polynomial vanishes, if I think I can define the function at that point where the denominator vanishes, it's going to have to be by factoring the numerator and the denominator and getting a cancellation. Let's look at an example. Define f of 1 in a way that extends the function f of s equal the quantity s cubed minus 1 divided by the quantity s squared minus 1 to be continuous at the point s equals 1. Notice that if I put s equal to 1, the denominator is 0. 1 squared minus 1 is 0. But the same is true for the numerator. If I put s equal 1 here, s cubed, that's 1 cubed is 1, minus 1 is 0. So both the numerator and denominator vanish at s equal 1. So when I look at the expression s cubed minus 1 divided by s squared minus 1, I realize that s minus 1 must be a factor of the numerator, and there's some other factor, and likewise s minus 1 is a factor of the denominator, and there has to be, of course, another factor. That's simple polynomial algebra. Anytime a polynomial vanishes at a certain point, the variable minus that point has to be a factor. So s cubed minus 1 vanishing for s equals 1 tells me s minus 1 is a factor. S squared minus 1 vanishing for s equals 1 tells me s minus 1 is a factor. Of course, in the denominator, we know that factorization easily. S minus 1 times s plus 1. To find the factorization of the numerator, what we can do is simply use division of polynomials to divide s minus 1 into s cubed minus 1. And when we do, we find the other factor as 1 plus s squared. So at this point, I have common factors of s minus 1 in the numerator and denominator, so I could cancel them. And I see that my expression originally given s cubed minus 1 over s squared minus 1 becomes the quantity 1 plus s squared divided by simply the quantity s plus 1, and that is valid for all s in the domain of the original expression. That, of course, means s not equal to 1. But When I look at this last expression, the quantity 1 plus s squared divided by the quantity s plus 1, I see that that is a continuous function on its entire domain. So consequently, look at the numerator. It's 1 plus s squared. That's defined for all real s. The denominator, s plus 1, is defined for all real s. And so the only problem is, where is the denominator 0? Well, that would be 0 only when s equals negative 1. So consequently, we now have a function which is defined and on a domain which contains the point s equals 1. That is, this expression right here is continuous on its domain, and its domain contains s equals 1. And so consequently, all I have to do is look and see what its value is at s equals 1, and that gives me the limit of this expression as s approaches 1, and tells me how to define f at s equals 1. So let's simply substitute in. We put s equals 1, we get in the numerator 1 plus 1 squared, in the denominator simply 1 plus 1, and so that's simply 3/2. And so now we see the way to define f at 1 is to simply require it to be 3/2. Now, f is continuous at s equals 1. With that extension of the function, look at this expression. We see it is still undefined at s equal negative 1. This gives us an extension to the whole real line with the point negative 1 removed. The function is now continuous on that larger domain. We know that when we look at an algebraic expression, it's going to define a continuous function on its domain just from our combination rules for continuous functions and the fact that f of x equal x is continuous. But sometimes we define functions using more than one algebraic expression. We put pieces together. And when we do that, we have to see that the function is continuous where we join the pieces. Well, let's look at an example. For what value of a is the function f of x given as x squared minus 1 for x less than 3, 2ax for x greater than or equal to 3, continuous at every x? Well, notice the only problem is right at x equals 3. For instance, if I were to take a number which is less than 3, a point less than 3 on the real line, then as the expression x squared minus 1 is continuous on the whole real line, it would be continuous at that point. If I take a point x greater than 3, the expression 2ax is continuous on the whole line, so it would be continuous at that point. Since the function is given by either one of these expressions, for x not equal to 3, it's continuous. So right off, I know f is continuous at any c not equal to 3. And so our problem is to examine how to choose a so that we get continuity at x equal 3. So let's evaluate, first off, the left-hand limit as x approaches 3 of f of x. So for x to the left of 3, f of x is given by the top expression x squared minus 1. So that's the limit as x approaches 3 from the left of x squared minus 1. Well, x squared minus 1, again, is a perfectly continuous function, and so its one-sided limits equal its two-sided limits. And so we're just going to look at the limit as x approaches 3 of x squared minus 1. Of course, that's 9 minus 1, which is 8. Okay, so now let's look at the other limit, the right-hand limit. That would be the limit as x approaches 3 from the right of f of x. That's the limit as x approaches 3 from the right of the expression that's valid to the right of 3, that's 2ax. So once we've had that expression put in, we can now evaluate the limit. So the limit as x approaches 3 from the right of 2ax, well, notice 2ax would be a perfectly continuous function on the whole line. And so its two-sided limits are the same as its one-sided limits. And so I can drop the little superscript plus. We're looking at the limit as x approaches 3 of 2ax. And so a is some number, and consequently the limit will just be what I get by replacing the x by 3. 2 times 3 is 6 times a gives 6a. And so consequently, what do we know about the requirement of a function being continuous at c equals 3? What we know is that it has to have a two-sided limit there, and that two-sided limit has to be the value of the function. So what is the value of the function? Well, remember, for x greater than or equal to 3, f of x equals 2ax. And so consequently, f at 3 is what we get by replacing x by 3 here. Again, that is the 6a. So what we see is our two-sided limit has to have the value 6a, but our left-hand limit has to have the value 8. For the two-sided limit to exist, both these limits have to be the same. They have to exist and be equal. So that means we can equate 8 and 6a, and then right away I see that the a itself is simply 8/6, or we can cancel 2's and arrive at 4/3 as the value of a. So a equals 4/3. When we make that choice for the number a, we get the left-hand limit and the right-hand limit of f of x are exactly the same. They exist, and so consequently we know the two-sided limit exists and has that common value, and so that gives us continuity for f at the problem point 3. Since it was already continuous everywhere else, we now have the function continuous on the whole real line. You've probably noticed that when you're graphing a continuous function on an interval, you can always draw the graph without lifting your pencil or pen up. This, in fact, has very useful consequences. Let's look. The intermediate value theorem for continuous functions. A function y equal f of x that is continuous on a closed interval a comma b takes on every value between f of a and f of b. In other words, if y naught is any value between f of a and f of b, then y naught equals f of c for some c in the interval ab. Notice what this is telling us. This is guaranteeing the existence of a solution to the equation y naught equal f of x. In other words, if I were to ask you to solve the equation y naught equal f of x, one question you would have is, does there exist a solution? Is there a solution of that equation? Well, if I know that the function f is continuous, and if I see that one of its values is bigger than y naught, one of its values is smaller than y naught, and the function's defined on an interval, then I know by this intermediate value theorem that the equation has a solution. This is often referred to as the intermediate value property for continuous functions. Let's look at a picture. Here I see a graph of a continuous function, and we know intuitively the idea of continuity for a function means there can be no breaks in the graph. And so here at the point b, we have the value f of b. At the left edge of the domain interval, we have the point a, and over here on the vertical axis f of a. Now, if you choose a point y naught on the vertical axis between f of a and f of b, notice you can come over and you have to hit the curve somewhere, and consequently when you hit it, you can go down and find a point C such that F at that C is the y naught. It would be impossible to get from this height up to this height without crossing the horizontal line at height y naught, unless I jump over it. Well, as soon as I try to jump over it with my drawing instrument, I have broken the continuity. So there is a picture illustrating the intermediate value property for continuous functions. Well, let's see how we can use the intermediate value property of continuous functions to prove an interesting fact about functions continuous on an interval. Suppose f is continuous on the closed interval 0, 1, and 0 is less than or equal to f of x is less than or equal to 1 for all x in the closed interval 0, 1. Show there is a point C in the closed interval 0, 1 such that f of c equals c. And note, this point C is called the fixed point of f. And generally speaking, it's often very useful to be able to find fixed points of functions in mathematics. And so this is sort of a very simple application of the intermediate value theorem. Let's look at a picture. Here, I've got a graph, and I'm showing the line y equals x. Here's the vertical axis y, which is the line x equals 0, and here we have the vertical line x equals 1. The x-axis, of course, is the horizontal line y equals 0, and here I've shown the dashed line y equals 1. And again, this diagonal line through that square, the unit square in the plane, is the equation y equals x. Now, our function f of x has domain the interval 0, 1, and its values all lie between 0 and 1. So if I graph that function, notice that's drawing a continuous curve that has to touch both of these vertical edges of that square. You can see from continuity here, there's no way to pull my pen across from the left edge to the right edge without crossing that diagonal line, y equals x. If that's the graph of f, notice its graph must intersect y equals x. And when I project down to the x-axis from that intersection point, I get a point C, which has the property that f of c is exactly c, because it's on the line y equals x. And so consequently, you can see geometrically that that has to be the case. Now, how can we prove this using the intermediate value property? So let's look at the function f of x. It has all its values between 0 and 1. And what I'm trying to find is a solution to the equation x equals f of x. And so that's the question. Does that equation have a solution? If it does, the solution, we'd call it c. C equals f of c would be our fixed point. So we take this equation and we write it as x minus f of x equals 0. So now we're trying to see if this expression, x minus f of x, takes the value 0. Well, let's call this a function, g of x. Notice this function g of x is continuous. It's the difference of two continuous functions. So let's look at its value at 0. G of 0 is 0 minus f at 0. Well, notice f of 0 is between 0 and 1, and so if 0 doesn't automatically work, then that would be because f of 0 is positive. If f of 0 is positive, 0 minus f of 0 is negative. And so consequently, if 0 isn't our answer, then g of 0 is negative. How about g at 1? Well, if 1 was our answer, notice g of 1 is 1 minus f of 1. If f of 1 equals 1, again, that could be our solution. If not, f of 1 has to be less than 1 because that's in the value f of x has to be between 0 and 1. So if f of 1 is less than 1, then 1 minus f of 1 is positive. And so you see what happens if we can put it this way. G of 0 is less than 0 if c, the point we're looking for, cannot be 0. G of 1 is bigger than 0 if the point c we're looking for is not equal to 1. So now if the solution is neither 0 or 1, we see we've got a continuous function g which is less than 0 at 0 and bigger than 0 at 1. So what's that telling us? Here's 0, here's 1. G is somewhere down here at 0, somewhere up here at 1, and so consequently by the intermediate value property, G has to take the value 0 somewhere in the interval. So now by the intermediate value property, I'll just abbreviate that, for continuous functions, there is c with g of c equals 0. Well, as soon as g of c equals 0, that means c minus f of c equals 0, and so c equals f of c. That is, c finally equals f of c, and that's our fixed point, guaranteed by the intermediate value property for continuous functions. Well, we've looked at the properties of continuous functions and how continuous functions can be combined to give more continuous functions, and we've looked at the intermediate value property for continuous functions and seen how it can be used to solve equations. Now that you've seen these examples, you might want to try some on your own.